You can start, sir.
Okay. Hello, good morning. So let's begin today's talk. So yesterday I discussed the Eddington limit and how to estimate the mass of the compact object at the centers. So in my view graph, few of the formulas were missing and there was a typo. So I just would like to go through few of the slides which I had already gone. So here is the radiation pressure force. How we derived this formula was not there in yesterday's presentation. So the L by 4 pi r square is essentially the flux crossing a radius r, where L is the luminosity from the compact object. Okay, and when we divide by h nu, this becomes the photon number flux. Okay, and when we multiply with the Thomson scattering cross section, then this becomes the number of scattering between the photon and the particles. And in each scattering, the momentum imparted is h nu by c. So when we multiply with this number with h nu by c, this becomes the radiation pressure force, which turns out to be the luminosity times the Thomson scattering cross section divided by 4 pi r square c, where c is the speed of light. And we need to equate this radiation pressure force with the gravitational force. Then we obtain the Eddington luminosity, L Eddington, from this equation, which is 4 pi c gm small m and divided by Thomson scattering cross section. Then we calculated this Eddington luminosity, and we had considered this small mass m, and we also said that electrons and protons are, of course, coupled with the Coulomb force. So when we need the mass, we need to put the mass of the proton, while the Thomson scattering works on electrons, but the gravitational force is obviously dominated by that on the proton. So we put the mass, this of course it has to be sum of this mass of the proton and electron, but this is of course approximately equal to the mass of the proton. So we replace m with the mass of the proton. Then we calculate the Eddington luminosity, which is 1.26 10 to the power 38 m mass in units of solar mass. So therefore one solar mass object, so it's the Eddington luminosity is 1.2 10 to the power 38. And because the luminosity, actual observed luminosity, has to be less or equal than the Eddington luminosity, so by using this inequality, we can estimate the mass given for a given luminosity L. The mass must be larger or equal to L divided by this 1.3 10 to the power 38 Amson. For a luminosity of L 10 to the power 46 ergs per second observed luminosity, then we derive the limit on the mass. That mass must be greater than 10 to the power 8 solar mass. So there was a typo here. I had written 10 to the power 6. Thanks to Professor Sekia, who informed about this typo. Okay, so that's about the Eddington limit. Let me now begin today's talk. So when we think of active galactic nuclei, of course, they are the centers and they are very complex object. Observationally, we already know we observed quite a number of characteristics in different bands. And when we try to understand agents, we need to understand all of this together through this central engines of active galactic nuclei. After lots of studies, we have come across so-called the standard paradigm or a standard model for AGN. There are several loopholes, but roughly we understand as follows. So at the center, there is a supermassive black hole with a mass in the range of 10 to the power 5 to 10 to the power 10 solar mass. And this black hole, supermassive black hole, may or may not be spinning, and of course there are lots of material in the galaxy, so it accretes the material from the galaxy. And of course the material will have or has certain angular momentum, the material cannot directly get created into the black hole, directly cannot come to the black hole, but it forms an accretion disk. So the material first spirals in the accretion disk, and gradually it radially moves radially inward and finally comes onto the black hole and disappears below the event horizon. This accretion disk is thought to emit the so-called the optical ultraviolet continuum, and if you look at the spectral energy distribution, which is shown in the lower middle panel, so we have a bump kind of emission color in blue color. So this is called the big blue bump, and this component is thought to be due to this accretion disk, and we will see in the next few graphs how such a component can arise from an accretion disk. Okay, and if you um, um, move inward, there are some regions called hot corona, very close to the black hole, and that corona gives rise to the X-ray power law component. We will also talk about that, but roughly understand that there is some kind of a harsh corona which with the temperature in energy units of about 100 kV, and that gives rise to this hot corona. If you come at the outer side after the accretion disk, there are supposed to be a torus kind of structure made up of cold gas and dust. What does this do? So this obviously, because there is a strong optical ultraviolet and X-ray emission, this torus is supposed to absorb these radiations and reprocess into the infrared. And here you see there is another bump which is called the infrared bump or IR bump. Okay, and in addition, there are certain things. For example, of course, there can be a jet originating from the very close to the supermassive black hole, and that can be observed in radio, of course. In addition, there are some of these clouds, so-called the broad line region clouds, which are closer to the black hole and compared to another kind of clouds, which are called the narrow line region clouds. The name arises because the broad line region clouds, closer to the ones which are closer to black hole, they are responsible for the broad emission lines in the optical UV. Yeah, I hope you remember the HL5 H beta lines with the typical widths of 5,000 kilometers per second. Here in the left side, you see this Cepheid-1 optical spectrum, this is spectrum of NGC 5548. You see this broad emission lines. This is H beta line. So this lines like this are supposed to arise from this broad line region because they are closer to the black hole. Therefore, they are moving faster around this black hole, and therefore the line width is larger. While the narrow line region clouds are further away from this broad line region cloud compared to this broad line region clouds, and therefore they are moving with much lower speeds around this black hole, and therefore the line widths are much smaller here. So the narrow lines arise from the narrow line regions, and broad line regions from broad line region clouds. And because of this complex structure, the spectrum, observed spectrum, depends on our line of sight or the viewing angle. For example, if our line of sight passes through this torus, this dusty torus, then the entire central engine, including the accretion disk, the hot corona, and the broadline region as well are blocked by this torus. So we do not see these broad emission lines in the spectrum, as well as we do not see the emission from the accretion disk. But some of the X-ray emission can penetrate, and we do see X-ray emission, particularly hard X-ray emission, are not absorbed by this cold dusty torus. Okay, and that is why, and while if the line of sight is not crossing this dusty torus, then we have a direct view of the central engine, including the the hot corona, the X-ray emitting region, of course, the accretion disk, the broad line region, as well as narrow line region. So you see the broad emission lines, the narrow emission lines, and the big blue bump as well here. Okay. Okay, so there are some other kinds of objects which I'll not go into detail here, this spectrum. Okay, but this is the overall picture of active galactic nuclei. And when we think of this central engine by mean the supermassive black hole and the eccentric disk, the inner jets and the hot corona responsible for X-rays. These structures, of course, observations require these things, and in some cases we do see some of these components, but the innermost regions are not possible to resolve. We cannot specifically resolve, and therefore we do not know the exact structure of these components. But from observations, uh, what has been deduced is shown in this view graph, and there are lots of uncertainty about the structure. But we think that, of course, there is a supermassive black hole, and around this is accreting, so therefore is an accretion disk, and there is a jet, particularly in radio loud agents. So in the bottom right panel there is this figure. So this is again, all of these are schematic, these are not real pictures. So we probably have this agent, so the supermassive black hole, the accretion disk, and the inner jet, so in something like this. This is a one possibility, of course. Or in radio quiet agents we may have the accretion disk and the supermassive black hole and the hot corona. It's shown, is schematically shown in the upper right panel. So these are just possibilities. These are close. This is what we think the structure may be in the inner regions. And of course, there are broadline region, and and then of course this dense torus is also there. And the entire the aim of our study or this talks will be try to understand how much we understand about the inner central engines of active galactic nuclei. So how do we probe observationally the innermost regions? So we have already seen that the variability time scale in the optical ultraviolet is about 1 to 10 days, which corresponds to, with the light travel time arguments, the size scale of about 0.001 to 0.01 parsec. While you see this X-ray variability time scale, that's about an hour or so. So this corresponds to size scale of about 10 to the minus 5 parsec. So this is already comparable to the Schwarzschild radius for black hole mass of 10 to the power 8 or solar mass or so. So that means if you want to study the innermost regions or the immediate environment of supermassive black holes, then we need to study X-rays. We need to observe X-rays, and that is why X-rays are important probes for study the inner central engines of radio quiet agents. And here is one example of X-ray light curve, how the X-ray emission varies as a function of time. And here you see the x-axis is in seconds, and you see the variability. Remarkable variability, sometimes by a factor of 2 in a very short time scale. So, now we know that X-rays are important probes for central engine. So how does the X-ray spectrum of AGN look like? So let's look at the right hand side panel here, and what we have plotted is the X-ray spectrum. In the x-axis we have energy in kilo electron volts, and in the y-axis this is the flux, X-ray flux in photons per centimeter square per second per keV. And essentially we are plotting the flux as a function of energy. Here we are plotting photon number flux as a function of energy. Usual in terms usual spectrum you would have seen, okay, the flux is a function of wavelength or frequency. So in X-ray the convention is that to plot in photon number flux as a function of energy. And when we look at the spectrum, what we see is that the spectrum is because this is a log plot, so a linear line looking thing is actually a power law. Okay, so from this plot it is clear that X-ray emission, X-ray spectrum from about 0.5 keV to few hundred keV is dominated by a power law component. But there are certain departures. For example, in the case of this AGN PG1416, you see below about 2 kb there is some kind of excess component, which we call a soft X-ray excess, and at high energy above about 100 kb or so, we don't detect enough photons, so it looks like the power law does not continue at high energy, but it cuts off at 200 kb or so. Same thing you can see in NGC 4151. Again, the power law does not continue at high energy band. Here we have better quality data, and the power law cuts off about 100 kb. And actually, getting high signals with noise data above 100 kb is difficult. These instruments are not very sensitive above 100 kb. So we have this kind of data only. And in the case of NGC 4151, you also see a cutoff at lower energy, and this is due to X-ray absorption. And we will see how X-ray absorption can create this kind of a cutoff. So what we see from the X-ray spectrum is X-ray emission from AGNs is dominated by a power law continuum with a high energy cutoff at few hundred kV. And such a spectrum is well described by the process called componization in the hot corona, and we will see this also briefly. And if you look at the spectral energy, this overall spectral energy distribution, you have already looked at, we have briefly discussed earlier, but here there are different components now. So in the optical UV band, we have this component in shown in the blue dash dot line. So this is our big blue bump, which I mentioned, that arises from the accretion disk. Then there is this power law component shown in this dash line. So that is the component, this power law with a high energy cutoff arising from thermal componization. In addition, we have another important thing, which is the soft excess below 2 kV, which I mentioned in the case of this PG object. So this is the soft excess component. And there are other features like line emission at around 6.4 kV that we call fluorescence K alpha line, and that is also very important diagnostics for regions very close to supermassive black hole, and we will also see that. These are the primary component from AGN central engines. And while at low energies, you see this infrared bump, that is obviously the reprocess emission in radio quiet type 1 AGN. And at radio range, of course, if the object is radio loud, we see the radio continuum emission, which can be variable. The subcomponent arises from the jets, of course. And in radio quiet emission, the radio emission is much lower, because the jet is either absent or extremely weak in these objects. So we will try to focus on these the primary emission, the accretion disk component, the soft excess, the power law, etc., from the central engine of type 1 active galactic nuclei. Okay. So we have a model for accretion disk, and that is the Sakura standard accretion disk model. So what happens in this model? The supermassive black hole at the center accretes material from the surroundings, and this material has certain angular momentum, so it cannot directly radially flow and directly dissipate in the black hole, but rather it forms an accretion disk. So it moves around the black hole, and as the angular momentum is lost gradually, this material flows, spirals in, and finally comes onto the black hole. This process generates geometrically thin and optically thick accretion disk, and the temperature of such a disk varies as a function of radius. So the innermost at the innermost radius, the temperature is highest, while when you go outward, then the temperature decreases as radius to the power minus 3/4. And the standard disk model allows to write down the temperature as a function of the accretion rate related to the Eddington rate, as a function of black hole mass, and as a function of radius, here in units of Schwarzschild radius. So this from this formula, you see, for let's say if an AGN is accreting at the maximum possible accretion rate, that is the Eddington rate, to produce the Eddington luminosity, and the black hole mass is, let's say, 10 to the power 8 solar mass. The M8 is in units of 10 to the power 8 solar mass. And let's say we try to measure the temperature at the source radius, then the temperature is about 6 into 10 to the power 5 Kelvin. Okay, and this temperature is obviously, and this accretion disk, as I mentioned, is optically thick, so it emits like a black body. So the inner disk has a temperature of about 6.3 10 to the power 5. So it will emit in the ultraviolet, extreme ultraviolet, far ultraviolet and extreme ultraviolet bands. And because the temperature varies as a function of radius, so the accretion disk can be divided in a number of annuli, and then an annuli with a smaller, very small width of this annuli, one can assume to be at a single temperature and emit like a black body. And then different annuli will have different temperatures according to this formula, the temperature proportional to the R to the power minus 3/4. And then you can calculate the black body emission from all these annuli, which is shown schematically in the right hand side figure. So the inner annuli, outer annuli, all are emitting at different temperatures, and then you finally sum all these black body spectrum from all the annuli, and finally form the accretion disk spectrum. Because the temperature, the maximum temperature is at the inner edge is given by this formula, so the spectrum cuts off at high frequencies, and you see this characteristic shape. And in the middle region, the shape of the spectrum is nu frequency to the power 1/3, and at the low frequency region, of course, because this is a black body, it's a religions nu square. So here it is in, and at high frequency, it will cut off according to Wien's formula, e to the power minus h nu divided by kt. So this is the characteristic spectrum of accretion disk. So if we happen to observe in the optical UV, far UV, and extreme ultraviolet bands, and then we derive the spectrum, and then compare with the accretion disk model, then we can test ideally we can test the standard accretion disk model. But in addition to this component, of course, there is a big blue bump, and various people have tried to match, and there are issues which I will not go into details. But the most importantly, the accretion disk spectrum cuts off around, let's say, around just below in the extreme UV or XUV region. It doesn't, only if the black hole mass is low, it can extend to softest X-rays, but you do not expect X-ray emission, particularly medium energy or hard X-ray emission from an accretion disk. But observationally, we do observe strong X-ray emission, which can go up to 100 kV, we just saw in earlier view graphs. So what is the process that gives rise to the X-ray emission? So this X-ray emission can be generated in this so-called this two-phase model. So we have, of course, the supermassive black hole and the accretion disk. And accretion disk, as we saw, so it emits this multicolor black body emission. In the inner regions, we think there is some thing called the corona, hot corona, with a temperature of about 100 kilo electron volt. So if such a hot corona is existing, then what will happen? So first of all, this accretion disk is emitting optical UV photons, and this optical UV photons are going in all the directions, and some of these photons are intercepted by this hot corona. What is hot corona? Hot corona will essentially have this hot electrons. So now there is an interaction between the low energy optical UV photons and hot or energetic electrons. So obviously, there is going to be inverse Compton scattering, and once these photons interact with one electron, there will be, depending on where do they go after the scattering, there will be multiple Compton scattering, and such multiple Compton scattering is supposed to give rise to X-ray power law continuum emission. To understand a little more detail, so take look at the figure in the bottom panel. So this is the curve in the red color is essentially the accretion disk component. Let's assume this is an accretion disk component. So what happens, this accretion disk emission, when it interacts with this hot corona, so a fraction, this optical depth of this hot corona is tau, so tau is about less than about 1. So a fraction tau of these seed photons. So take a fraction which is less than 1. So this will become smaller. The amplitude will go down, and that fraction is upscatter to energies by a factor given by this 1 plus 4 kT by MEC square. This comes from the physics of quantization. And one scattering step, so one of a fraction tau of this accretion disk black body is scattered to higher energy. So this component amplitude reduces and then it moves to higher energy. Then in the second scattering step, another this again the same fraction tau is taken and upscattered to higher energies by the same factor 1 plus 4 kTe divided by MEC square. This steps continue until the photon energies reach close to the temperature of this hot corona, because beyond that there are not enough electrons to upscatter to higher energies compared to the temperature of hot corona. So now if you have in different scattering steps, you have this kind of black bodies, and if you sum over all these black bodies, so then what you'll see a power law with a high energy cutoff, and this cutoff will be at about the temperature of the hot corona. So that's how we get a power law continuum with a high energy cutoff. And observationally, do we see this kind of cutoff? Yes, we see this kind of cutoff. For example, these are observations with NASA's New Star mission. New Star mission is a very important X-ray mission, which it carried for the first time the hard X-ray mirror. So one could focus hard X-rays, just like the soft X-rays, up to an energy of about 80 kV or so. So this focusing telescope resulted in high signal to noise. Because of the focusing optics, one could reduce the background drastically. So here is some of the data. So this data has been compared with a simple power law model as well as a reflection model to take into account the iron K alpha line. And we will see this another kind of reflection component. But when you model the data with power law model and reflection model and take the ratio of data and model, if power law model and reflection were good enough, then this ratio would be 1 everywhere. But what you see here, the ratio is 1 up to about 20 or 30 kV. Beyond that, there is a deficit of emission compared to this power law model, and that is the signature of the cutoff or cutoff high energy cutoff. Okay, and after you introduce a high energy cutoff, then this ratio is very close to 1 at all energies. And this cutoff is obviously the signature of the temperature of the compromising corona. So therefore, one can measure the temperature of the corona, and in this case, it turns out to be about 61 kV, optical depth of about 0.7 or so. So this is a signature of thermal componization for X-ray emission in active galactic nuclei. And if you look at in little more detail, the spectral distribution in X-rays, so it looks like this. So again, this is log-log plot. This side it is EFE. Its y-axis is missing, but E energy times the flux density Fe is plotted as a function of energy. So in this plot, a constant is essentially a power law of photon index 2. Okay, because this is a log-log plot, and we are multiplying with the energy to the flux Fe. So constant is power law, essentially a power law of photon index 2, and this entire spectrum is dominated by a constant. Of course, there are departures from this. What are the departures? The very lowest energies, there is a soft X-ray excess, and around just below 1 kV, there are a large number of this absorption features, absorption edges, absorption lines, etc. So there is a deficit of emission there. We will see how these things arise. Then at around 6.4 kV, there is this 6.4 this iron K alpha line, which is, as I mentioned, is an important diagnostics, and we will also see this line. And then at around 20 to 30 kV, there is a hump which is called the reflection hump, and at high energies, this high energy cutoff due to thermal componentization. Okay, so let's see. Look at this this absorption features. Why do such absorption features arise in this setting? So here is an example of the X-ray absorption spectrum of Seyfert galaxy NGC 3783, and this is real data taken with Chandra X-ray Observatory, and this object was observed for about 12 days or so. So from the continuous 12 days observation, this is the integrated spectrum. So this spectrum has a very high signal to noise, and this is high resolution X-ray spectrum taken with X-ray gratings on board the Chandra mission. And this may look like to you, these are all kind of a noise or something like that, but no, these are actual signals. So these are highly significant absorption lines, absorption features. They are not actually noise. There is this lower panel is an expanded view to show from 0.4 or 0.5 kV to about 1 kV to show various absorption lines and features. And some of these were actually not known from atomic physics. Only when these features were observed in X-rays with a spectrum of AGN, so then people figured out what kind of atomic physics or what kind of atomic transitions can actually result in some of these things. And that's how the astrophysics also helps atomic physics to find the atomic transitions, etc. Okay, so. And I'm sure you will recall the optical UV spectrum. When we saw some of the emission lines, H alpha, H beta, H gamma, H delta, oxygen 3, sulfur 2, all these emission lines. But there were a small number of emission lines. We could clearly distinguish with the emission lines and the continuum. But here you see numerous absorption lines, so many of them. So that is one difference here. There are so many transitions happening in the X-ray, in the soft X-ray band. It is just from 0.5 kV to about 9 kV. In this band, you see huge number of transitions. How does it occur? So it occurs because of some kind of absorbing cloud. So we have the AGN central engine, and maybe some cloud is located along the line of sight. So the X-ray emission arising from the central region passes through such a cloud, and that cloud has, of course, various elements, and those elements, due to the atomic transitions, because of this radiation, X-ray radiation, and this cloud absorbs and puts the signatures of all the elements and various ionization stages, and according to the abundance of various elements, you see this characteristic complex spectrum. And why so many transitions? And if you look at the X-ray band, let's say 0.2 to 10 kV. So in the X-ray band, look at the carbon, nitrogen, oxygen, neon, all these elements up to iron. The transitions fall into this, particularly the iron K band. What is iron K band? So let's say take the example of iron atom. So iron atom, because of the N equal to 2 to N equal to 1 transition, that produces this the K alpha line at 6.4 kV for neutral iron. But if the iron is highly ionized, like hydrogen like iron, that means only one electron is there as a part of the atom. So then to remove that last electron, it takes about 9.1 kV. So from 6.4 kV to 9.1 kV, that is the iron K band. And in this band, so neutral iron, that means all the 26 electrons in the iron, and then ionized iron, you remove 1 electron, 2 electron, like that, all the way to 25th electron. So all the ionization stages of iron are there, and for each ionization stage there are these transitions, K alpha transitions, then absorption edges, etc. So for one iron atom, there's 26 ionization stages and atomic transitions for each of them. All these fall in this band, and not only for iron, the K bands of carbon, nitrogen, oxygen, neon, magnesium, all these elements up to iron fall in this X-ray band. So many elements, so many ionization stages of each element, and for each ionization stage, so many transitions, all these things fall in X-ray band. Not only iron, K band, not only the K band of various elements, but the L cell transitions of all these elements from silicon to iron also fall in this X-ray band. That is why we see so many transitions, so many absorption lines in the X-ray spectrum from 0.2 to 10 K. So how does the photoelectric absorption? Okay, I think few things are missing here. Okay, but let me explain. So look at this figure. So again, we have a power law component, and depending on the absorption column, so if the lowest absorption column, if you introduce, then this power law cuts off here. If you increase the absorption column, this is the amount of absorbing material, then power law cuts starts cutting from at higher energy, and you increase further, then this X-ray power law cuts off even at a higher energy. The last one is for about 10 to the power 24 percentage square column density, and here the one which cuts off around 0.1 or 0.2 or 0.3 kV, that is I think about 10 to the power 20 percentage square column density. So what is happening here? Well, of course this absorbing material has various elements, and each of these elements results in absorption edges. For example, you see here in the green curve, this absorption edge at around 0.6 kV is due to oxygen, neutral oxygen, and at around 7.1 kV, you see the absorption edge due to iron K cell. So these are the locations where this absorption edge is there, and therefore the photons with slightly higher energy, all of them are being absorbed, and therefore you see this characteristic absorption edge structures. And this is due to the neutral material. You see only absorption edges, no absorption lines here. Okay. But the moment you introduce ionization of the material, of course, there will be transitions to higher level as a result of the absorption, and you start seeing the absorption lines. The curve, the spectrum in the red curve, that is almost neutral, so you only see absorption edges. But when you increase the ionization level, so you will start seeing this absorption lines. And for highly ionized, you see lots and lots of this absorption lines. These are generated with models. Okay, and if it is almost fully ionized, then you again, because now the electrons are no longer bound, so they cannot make transitions to higher levels. So you will see no absorption lines in fully ionized plasma. Okay, so this is about the absorption lines. How does this numerous absorption lines and edges arise in the X-ray spectrum? Now let's look at this soft X-ray axis component. So you see, and the soft axis is observed below 1 kV. This is again the data to model ratio, where the model is a simple power law. So when you compare a power law with the observed data, you start seeing this excess emission below 1 or 2 kV. And when you model this with a simple black body, you can describe, but the temperature turns out to be 100 to 300 electron volt. But even though it looks like a multicolor black body, but this is not due to the intrinsic emission from accretion disk, because the temperature is much higher compared to what is expected from an accretion disk around a supermassive black hole of 10 to the power 7, 10 to the power 8 solar mass. So this origin has been a puzzle, but we have certain models which I'll not go into details. Another important component is the iron K-alpha line. So here are some of the examples of the iron K-alpha line profiles. This is from the XMM Newton observations of iron line, and here you see there is a narrow component at 6.4 kV, and in addition there is a broad component, and the narrow component is not really resolved, but the broad component is clearly resolved, and it has a full width at half maximum of about 50,000 kilometer per second, compared to the optical UV broad emission lines, which are just 5,000, around 5,000 kilometer per second. So in this particular case, it is roughly 10 times, the width is 10 times larger compared to the width of optical UV emission lines. This is the same, the broad iron line, but with the different observations, much higher signal to noise. So you see this iron K-alpha line as well as K-beta line, and this broad line with this red wing. So one question, obviously, you may think, okay, why such a large width? So we will see this why such a large, how the large width can actually result from AGNs. So this, the iron K-alpha line and as well as some of the soft X's we discussed earlier can arise due to some process called reflection. So X-ray reflection. So let's see what exactly is this process. So first of all, we have this hot corona, and as we know, this hot corona emits the X-ray power light spectrum as a through this quantization process. And the power law emission can, of course, goes in all directions, and some fraction also illuminates this accretion disk. And accretion disk is a thick, optically thick material, so it can act like a mirror. So it reflects some of this X-rays, and of course, this reflection is not like our similar or a mirror which we use in daily life, but there are interactions. Some of them will absorb. There will be some signatures which will be generated in the accretion disk. And what are these things? Let's look into this. So let's imagine photons, X-ray photons are interacting with the material in the accretion disk. So there are several possible outcomes in such a scenario. First of all, the accretion disk temperature, given the accretion disk temperature, the hydrogen will be ionized protons and electrons, but other elements will not be fully ionized. So of course, there will be some free electrons. So this compton, so X-rays will get compton scattered by the free electrons in the disk. So because of this free electrons, this free electrons will act like a mirror and reflect the power law into a power law only. Okay, then some of the photons, because there are these heavy elements like iron, carbon, nitrogen, etc., have bound electrons. So there will be photoelectric absorption of some of these X-rays. And whenever there is a photoelectric absorption, so there will be fluorescence line as well. So for example, look at this iron atom. So as a result of the absorption of photon above 7.1 keV, there is a vacancy here because the electron has been removed, and the ion is in excited state. Then quickly another electron from the L cell jumps into K cell, and this produces this iron K-alpha line at 6.4 kV. Similarly, the other lines due to nickel, chromium, etc. are expected, but the iron has the largest cosmic high cosmic abundance as well as the high fluorescence yield. These two combination of these two produces strong iron K-alpha line, while all other lines are much weaker. Okay, so this figure is essentially a simulation where a simple incident power law. So what we are achieving here, a simple power law spectrum is illuminating this accretion disk, and this accretion disk reflects. Then that reflection spectrum has this kind of signatures. Okay, of course, this fluorescence lines due to iron and other elements. What are the other features? For example, you see a hump-like thing at around 20 kV. This is because of two processes. At the lower side, at the lower energies, because this at 7.1 kV, there is an absorption edge. And because of this absorption edge, you produce this curvature. Near the absorption edge, lots of photons are absorbed. But if you move away towards high energy from the edge, then lesser and lesser number of photons are absorbed. And by the time you come around 20 kV or so, there is almost no absorption. But at very high energies, due to the Compton recoil process, the high energy photons lose their energy and move to lower energy. And as a result of this phototic absorption at lower energy and Compton recoil process, you see this hump, which we call reflection hump. So this process is this spectrum is the reflection spectrum, where we have the edge due to iron K edge, and then fluorescence lines due to most importantly iron and even other elements, and this hump emission hump at around 2030 keV. Okay, and because the accretion disk is accretion disk can be very close to the can extend very close to the black hole, and if the iron line is arising from the inner regions in the accretion disk, then the line will be modified due to the strong gravity due to this black hole and high speeds or special relativity in the innermost regions. And let's see how these two things can shape the line. So let's imagine this is our accretion disk, and there are two rings in the accretion disk. And let's see these two rings are emitting this line photons. And because the disk is rotating, if you just apply the Newtonian physics, so you see in the rest frame of this thing, it will be like a delta function. But because of the rotation, the observer, and if you just apply Newtonian physics, this will see a double horn kind of a profile. Now, if you apply special relativity and imagine the disk is rotating in the anti-clockwise direction. So in the right hand side, it's moved. Or no, so let's imagine that the disk is rotating in the clockwise direction. So in the right hand side, disk is actually approaching towards us, while the left hand side is moving away from us. And because the speeds are relativistic here, and therefore due to the beaming effect, the emission from this right hand side will be enhanced. So the blue wing gets stronger, while the red wing, the emission from the red wing is beamed away. So therefore the red wing becomes weaker, and this is due to special relativity, due to high speeds only. Now, because of strong gravity of the supermassive black hole, there will be the effects of general relativity, and most importantly, this gravitational redshift. And what does this do? So this will shift the line to higher energies as a function of energy. So you see this strong red wing due to general relativity here. And finally, if you sum the line emission from all the rings in the disk, then the line profile looks like this. So you have this blue peak due to relativistic beaming, then you have a red peak, and then a strong red wing due to gravitational redshift due to general relativity. And such a model actually describes the data very well. This is the X-ray spectrum iron K alpha line profile observed with the Japanese mission Advanced Satellite for Cosmos and Astrophysics for the first time. And this is the model fitted in the red color to this data, and you clearly see that a relativistic accretion disk fits the data very well. They fits the line profile very well, and that's why we think this iron K alpha line, one can probe the innermost accretion disk in active galactic nuclei. And because if the disk, depending on where exactly the disk extends towards the black hole, if the disk extends very close to the black hole, there will be a stronger effect of general relativity as well as special relativity due to the speeds. And the inner radius depends on the black hole spin. For example, if the black hole is not spinning, if it is a fossil black hole, the inner radius is at 6 times Rg, where Rg is the gravitational radius, Gm divided by c square. While if the black hole is spinning fast, if it is a maximal curve black hole, then the disk can extend almost close to 1 Rg, to be specific 1.235 Rg. So if and now if you look at the iron K-alpha line for the accretion disk around these two kinds of black hole, in the Schwarzschild case, because the disk extends up only up to 6 RG, so it has a weaker red wing, because general relativity is not very strong here at 6 RG. But if the disk extends to almost close to 1 RG, or much closer to the black hole, that means then the red wing becomes stronger, and then the red wing of the line can extend to be below 4 kb, up to 3 kb, 3 kb also. So by observing the lines and by measuring the red wing, then we can determine the inner radius of the accretion disk, and therefore the black hole spin. And this technique has been used in a number of AGNs to measure the black hole spin. And anywhere you come across, okay, the black hole spin measured with iron K-alpha line is this much, then this is a technique being used. Okay, and the entire reflection spectrum. So this is again a simulation. So in the black curve shows the reflection spectrum unmodified due to these relativistic effects. But when you modify the spectrum with relativistic effects, then see the changes. For example, this narrow iron lines becomes much broader, the red wings become stronger. There are several features in the soft X-ray band, and because of the relativistic blurring, it becomes much more smoother. Even the reflection hump, the shape changes. And here are the examples of such observations. You see this soft X-rays, the broad iron line, the reflection hump, and these are real data. And you compare with these models here. So we are definitely observing relativistic effects in the X-ray spectrum, and this is a really nice example of observation of this AGN Markarian 335 with new star. And here is the data. You see the white circles here, and these are the models. So the blue line represented here, this is the model without the relativistic blurring, that is unblurred model, while the yellow color is the blurred reflection model. And see how well this relativistic blurred model describes the data, both iron line, the red wing, etc. So this is a definite signature of extreme relativistic reflection in the X-ray spectrum of active galactic nuclei. This is the one of the broad iron line based on long observations with the extreme Newton, and you see the characteristic broad iron line in the profile, and this line extends down to about 3 kV or so. And one has measured here the black hole spin, and it turns out that the black hole in this AGN is highly spinning. There is another important progress in studying the relativistic effects in the AGN spectrum. So because the X-ray power law continuum is illuminating the accretion disk, and a reflection and then getting reflected. So when you compare with the direct continuum and the reflection spectrum, there is expected to some time delay. Okay, so this has, and now with observations we can measure such time delays. For example, let's look at this is the spectrum, X-ray spectrum, again the data to model ratio. So in this case, in addition to iron K-alpha line, there is iron L line, again arising from the accretion disk. So you separate out the bands where the reflection dominates. For example, here the iron L line, because there is a high signal to noise here in this band. And then the pure continuum here, there are no lines here. And then these two things you cross correlate. So using a technique, one can measure this lag as a temporal frequency. This temporal frequency is essentially one by time. Okay, so this is a lag between this continuum and this line as a function of this temporal frequency, and at some frequency just above 10 to the minus 3 hertz. Here you see there is a lag where this negative lag essentially means that this component, the reflection component, is delayed compared to the primary emission. That is what you expect. So this delay is essentially called the reverberation lag, and this is again a source or signature for the reflection process which is occurring in active galactic nuclei. Okay, I think I have whatever I wanted to say here, I have said. So we have 6-7 minutes, so we can actually have a discussion or questions here. Okay, so open for questions now. Questions, please.
Sir, am I audible?
Yes.
Thank you, sir. So my question was, what is the matters or what are the points that dominates the formation of the disk across the axial region? Like when the matter is coming onto the black hole, it has full liberty to fall in any direction. So what dominates that the disk will form in this axis only and not in any other axis? Is it the momentum and the spin of the black?
Angular momentum of the material being being accreted. Okay, so that decides the inclination or the in which direction or in which plane the accretion disk will be formed. So some, for example, in fact, because of this only, if you look at let's say spiral galaxies. So spiral galaxies, of course, the galaxies has a disk, and therefore there is a plane defined by the disk, and the AGN host state, of course, will have an accretion disk. So the accretion disk and the galactic disk are not necessarily in the same plane there. So it depends on the angular momentum and the AGN. These are very complex things as well, because how exactly the AGN is being fueled, whether due to its mergers or etc. So what is the initial angular momentum of the material which is being accreted? Depending on that, the accretion disk will be formed.
Okay, so it is dependent on the material that is coming in.
Yes.
Okay, thank you, sir.
Yeah.
Sir, actually, I have a second question, if I may.
Yeah, sure.
From the AGN paradigm, the photo that you just showed, the coronal outflow layer, it is just in the formation of a jet. It's showing as a jet. So is it like the coronal outflow is in the jet motion? Is it like that?
A good question. So as I was mentioning, we do not exactly know the geometry of the disk and corona. So one possibility, particularly in radio loud AGNs, or even in if you have heard about black hole X-ray binaries, in certain state of black hole binaries where these objects show jets. So in such a case, the base of the jet may act like a corona. Okay, but we are not very sure. So it is possible. One possibility, the base of the corona acting as a jet is one possibility. We are not sure about that. Or it is in radio quiet AGNs where there are no jets, then maybe the inner region is just becomes like a hot corona. And in some cases, the accretion disk is truncated at several RG, maybe 50 RG or 20 RG. So the inner regions may also be filled with the hot corona. So that is where we are not very sure about the geometry. And this is what many people are actually probing.
Okay. Yeah. Thanks.
Yeah. Any other question?
Gulab, there are a few questions on the chat box.
Okay.
You want to have a look? Yeah.
Okay, so let's begin. Okay, I think first question I have already explained. Okay, so how do we know? Vaibhav is asking, how do we explain the presence of cold gas around such a strong source of energy. So when we are talking about cold gas, of course, very close to the black hole, the accretion disk and hot corona, finding cold material is not there. But when we are saying the dusty torus, which is cold, that is quite far. In fact, let's say the broad line region clouds are located at around five or tens of thousands of gravitational radius. If you look at the time delay between the broad line region clouds, are the broad emission lines, and the continuum emission, which is coming from the inner region, that can be days, several days. So the light travels for several days, then it reaches to the broad line region cloud, and the torus is even beyond that. So the torus, the cold dusty torus, is not very not very close. But of course, the accretion disk is also not fully ionized, and accretion disk we call generally cold accretion disk, but that can exist because the temperature is only about a few electron volt, maybe up to at most few tens of electron volt, in the innermost regions. And if you move outer regions, the temperature of course decreases, and the outer disk of course even can emit in the near infrared optical. Okay. Okay, so Jyotirmaya is asking, black holes absorb matter and radiation due to its huge gravity. Therefore, its energy should increase gradually to infinity. Then also how its temperature is very low, that is 10 to the power minus 8 Kelvin. So first of all, I didn't talk anything about below event horizon. What we are talking outside the event horizon. So 10 to the power minus 8 Kelvin, I didn't say anywhere such a low temperature. So outside as I mentioned, the accretion disk has a temperature of few tens of electron volt. I think you mentioned the hot corona is about 100 kilo electron volt. That will be about 10 to the power 8, 10 to the power 9 kelvins, not 10 minus 8. And anyway, we cannot probe below the event horizons. We don't talk about the regions below event horizon when we are trying to probe observationally. Another question from Khushbu. So what is the difference between type 1 and type 2 AGNs? So this classification is based on the optical ultraviolet spectrum. If an AGN shows both the broad emission lines with the typical widths of 5,000 km per second, as well as narrow emission lines with typical widths of 500 km per second, then such AGNs we call type 1 AGNs. So you see broad emission lines in type 1 AGNs, but if the AGN only shows narrow emission lines, no broad emission lines, then we call such AGNs as type 2 AGNs. Okay, I think Professor Sekke has already answered this. What happens when an object crosses the Eddington limit? So Eddington limit is in. There are certain assumptions. First of all, this is in spherical geometry, and one applies only Thomson scattering. So in this case, if the object crosses the Eddington limit, so then in that case the radiation pressure force will dominate gravitational force. So there, of course, this will result in outflows in the form of winds, etc. And the moment it again the radiation pressure reduces, when some material is thrown out, then it again will come down to the sub-Eddington region. But whenever Eddington limit gets exceeded, of course radiation pressure force will throw out the material. So these different Mohammed say us these differences, different observables present us from directly comparing the intrinsic properties of two types of AGNs. You mean probably Mohammed means the presence of torus ejecta, where which obscures the central region, and then in such cases, finding the intrinsic emission, properties are difficult. Yes, to some extent it is difficult, but the obscuration is very effective at one wavelength, but may not be at other wavelength. As I was mentioning, the X-rays, medium energy X-rays and hard X-rays are not actually penetrate such obscuring torus. So we still study some part of the central engine, but not entirely. For example, we cannot probe accretion disks in type 2 agents directly, but there are indirect ways. For example, even we can observe broad emission lines in type 2 agents if you look at in polarized light. So once we look at the broad emission lines and then what kind of continuum may be generating such broad emission lines, it is usually possible to infer indirectly the intrinsic continuum of these agents as well, but not entirely. Tanmay is asking why there has a large number of frequency correspond to iron. Is it it means that iron can be in any of its ionogen state from neutral to 26 plus? How you can distinguish between two absorption spectra from two elements in the same energy range? So yes, because iron of course has 26 electrons and it can be in several different ionization stages, and each ionization stage will give a number of transitions. That's why we can have large number of transitions from iron. And the transition, the spectrum, or the transitions between different energy levels are specific to a particular ionization stage of an element. So by looking at the number of transitions and comparing with the lab spectrum of that particular ion, we can figure out, okay, this particular set of lines are actually arising from this element in this ionization stage, and that is why we can differentiate the two different spectra, and we can measure the ionization stages of absorbing material. Abhay says this spectrum has been taken over the entire disk. Can we resolve the spectrum from individual regions of the disk around black holes? No, we cannot resolve this because we cannot even resolve the accretion disk. So we cannot separate out the emission from different parts of the region. This is from the entire, whatever we observe is from the entire disk. Tanmay says intensity versus energy plot. The curve plot is steeper. Which plot? I'm not sure which plot he is mentioning. I am not sure which curve plot he is mentioning. So, who is asking this question? Abhay, I think. Can you repeat the question, or can you detail the question? Tanmay is asking this question, intensity versus energy plot. The curve plot is steeper. Why? So can you elaborate a little more on this question, Tanmay? Tanmay not there. So I'll move to next question. Preeti is asking, can you explain the difference between the hard and soft lag? So as I mentioned, the soft lag is due to the reverberation lag. So the reflection spectrum is delayed compared to the continuum or illuminating emission. Soft lag, that is the reason. I did not discuss about the hard lag, where the soft emissions are arriving earlier compared to the hard emission. That is why we call it hard lag. So hard lag is supposed to be due to the continuum. So when we are looking at the soft X-rays and the hard X-rays, so first the soft X-rays changes, soft X-ray varies, then it is followed by hard X-rays, and this is due to something called propagation fluctuation model, where the the variability at longer wavelength is at slower because they are arising at further away in this corona region, while if you go to higher and higher energies, these are coming closer and closer, and the variability or whatever fluctuations which are propagating, they become faster and faster. Okay, this is one of the model, but very clear understanding of the hard lags is not there. I mean, this is a more like a qualitative explanation. How conservation of angular momentum can explain perpendicular ejection of jets. So first of all, this angular momentum, when it forms an accretion disk around the black hole, then it obviously defines a symmetry axis is perpendicular to the accretion disk where the jets arise. Is it possible that AGN can produce only one jet in one direction only? If there is nothing in the external medium, for example, let's say initially there are jets in both the directions, but maybe in the one side there were some kind of an external medium which suppresses the jet, or therefore this is not observable. That kind of thing may happen, but intrinsically it is to me it looks impossible to produce one-sided jet. But of course, observationally there are lots of effect, and one can see only one-sided jets. For example, the one which is closer to the line of sight, and which where due to the beaming you will see that jet, but the one which is moving away you will not see the jet. But it is not because the jet is not there, but essentially it's a relativistic effect. Okay, the K alpha line of iron in two different disks in black holes outside, where you define the variation in with the spin parameter. Not clear to me. So what I wanted to say there, that the inner radius of the accretion disk depends on the black hole spin, and the iron line profile depends on the inner radius. Because if the disk is extending very, very close to the black hole, then obviously there will be a strong relativistic effect. If the disk is further away, if the disk is, let's say it's because of the Schwarzschild radius, it is truncated at 6 RG, then relativistic effects will be weaker, and therefore iron line profile will be different. And this fact one can use to measure the black hole spin. I think I have covered almost all questions.
Gulab, I think Dewangan is also there. We will try taking a screenshot.
Yeah, sure. Yeah. So I'll stop this.
You can stop sharing here.
Yeah.
Right. So I wanted to check if we can do the screenshots and how they work out. And
okay.
So that tomorrow I have asked all the participants to sort of come for the screenshots if they can. So Sagar, are you there?
Yes, sir.
Yeah. Okay. So I'm trying to take the screenshots. Can you give me some pointer of how to increase the number of the grid blocks on the Zoom? Right now I have 1, 2, 3, 4, 5, 25 by 25. How do I increase to smaller windows and pack it more? Is there any option to do that?
No, this is standard, sir.
25 by 25 is standard, is it?
Yeah.
I read somewhere you can increase to 49, 7 by 7, but that is not possible then. Okay, so I request all the participants to turn on their videos And Sykes, you said that you had some issues regarding the videos turning off after a while.
I don't know. Today it seems to be working fine.
Okay.
Maybe they said change the settings. I'm not sure. But
Right.
today it seems to be fine. Yeah.
Okay. So thank you all for turning on your video. We'll just start taking some screenshots and let you know when we finish. So this is just a run for tomorrow's screenshot. Okay, I seem to have completed on my desktop. Sykes and Sagar, if you also are taking screenshot, let me know when you finish. We can let the participants have a break. I have 4 windows. Sykes, are you done with the screenshots?
Yeah. I think I just tried out. It seems to be fine, but I can't go beyond that 49 actually.
How did you go to 49 people on your screen?
49, you have to change the settings.
Okay. I'll talk to you later about that.
We'll do it later. Yeah. Sure.
Okay. Thank you everyone for turning on your video. We'll join back at 11:30. And thanks a lot, Gulab, for the.
Thank you. Bye.
Sykes, if you are online,
Yeah.
can you tell me now what did you change in the settings to get it 7x7?
Actually, what happens is that in that Zoom, not where it is broadcasting, but you have the Zoom window which shows your so where you have your profile thing.
Okay.